In this video, I will present how to use state machines and state machines diagrams for embedded system design. This video will have 3 parts. In the first part, I'll do introduction. I'll talk about what state machines are and how to draw a diagram of a state machine. In the second video, I'll do an example. I'll do a modeling of a non-technical system to show that state machines can be used to model any kind of system. And in the third video, I will do a second example, and I will design and model a button debouncer. This is a very useful algorithm, and I'll also show how to implement it for Atmel AVR in the C programming language. So let's start with the first part of the video. Introduction to state machines. So what are state machines? Well, it is a system modeling technique. We can define a behavior and function of a system. The advantage of this approach is that it can be very conveniently arranged in a diagram, right? And whatever is in a diagram, it's very easy to see the function. We can imagine the behavior of the system, and we can also very easily think about it. If the diagram is laid out very nicely, the problems in the design can be very easily spotted. It's definitely way better than looking at pseudo or source code and trying to find bugs. Also, state machine diagrams follow some rules. That has the advantage that other people can read and understand the diagram. Also, it's very intuitive and simple, so even people who do not write code can look at your system design and understand it. The third main advantage is that state machine diagrams can be very easily translated into programming code. There are some simple techniques for converting the diagram to code. This conversion is very mechanical, and you can directly do it following just the simple rules. Then the probability of making a mistake is very small. My entire talk and my state diagrams are based on the concept on finite state machines, and I also borrowed some notation for UML state chart notation. So if you want to know details, you can search for these terms. So let's start with the introduction. What is a state? State describes the condition the system is in. It's a condition at a moment. So, for example, a switch has 2 states. It is a binary state machine. It can be either turned on or turned off. A 7-segment LCD display has 11 states. It can be off, or it can show numbers from 0 to 9, which is 10 states. So we have 1 state off and 10 states for numbers. So we have 11 possible states altogether. If we look at something not related to electronic, for example, a simple egg, the egg can be in 4 states. When you buy it, it's raw. If you boil it for a little bit, it will be soft-boiled. If you keep boiling, it is hard-boiled. Or if you just leave it on your table, it will get spoiled in 1 week. So we can model an egg as a system that has 4 different states: raw, soft-boiled, hard-boiled, or spoiled. There are 2 important things to note here. So first, the system can be only in 1 state at a moment of time. So it's impossible for the switch to be turned on and off at the same time. Right? So the system can be only in 1 state. And secondly, each state has a unique name. The switch can be on or off, egg can be raw or spoiled, display can be showing 1, 2, 3. Having unique names is important for good organization of the state machine. How do we represent states graphically? So states are represented as ellipses with the name inside. So here is an example of a state machine for a display. So display can be either off or it can be showing 1. So we have two different here on the screen there are two different states of the 7-segment display state machine. One of the states has a special meaning. It is called an initial state. This state is the state the machine is when you turn it on. So when you plug your machine to power, the first state it takes immediately after reset is called initial state. In the diagram we mark the initial state with an arrow pointing to it from a word reset or initial or something like that. So here the initial state is marked using arrow and a word reset. So when you turn the machine on, the display will be in a state display off. So now let's do an example. Let's have a look at this switch. So how can we model it? So switch has two positions, so it's a binary, and it can be either on the bottom position or in the top position, right? So we have bottom, or we can have top. I said that states are in ellipses, so I'll draw the ellipses. So we have our bottom state and we have our top state. Now, an important thing to do when you design a state machine is to decide which state is initial. So let's say when you install a switch, it will be in the bottom position. So we will mark it like this. Reset. Right, and now we know that this machine after is initialized is in the bottom state. Now, activity. So each state can have an activity specified. An activity is a statement which is true while the system is in the state. In other words, it is work that's being done while the system in state. It's done all the time. So as long as the system stays in this state, the activity is done. So let's have a look at the 7-segment display. Here we have these statements. So if the state is off, then all the segments are off. So this here, all the segments are off, is the activity associated with this state. So as long as the state is off, then nothing is showing on the display, all segments are on. Now, if the system is in a state showing 1, segments B and C are on. So the display has these segments here. So these segments here are on, B and C, and the display is showing 1. So this is the activity associated with the state. How activity is represented? It's written inside in the ellipse together with the state name. So here we have an example of a we have an example of a LCD 7-segment LCD system. So we have two states shown here, and is display off and showing 1, and the statement and the activities are shown in the ellipse together with the state name. Okay, let's continue with the example of the switch. We will add some activities to this system. So whenever the switch is in the bottom position, we want we want the light to be on, right? So the statement that holds true while the system is in the bottom state is that the light is off. So light is off, right? And whenever the switch, the system of a switch is in the top state, the light is on. So light is on. So these are the activities that are associated with the two states in our example of a switch. Now, the state can change, right? When you press the switch, it changes from off to on, or if you boil the egg for 4 minutes, it changes from raw to soft boiled. This is called a state transition. State transition consists of an origin state, a condition, and a destination state, right? So the system takes this transition only when the condition is met. So for example, for the switch, the condition here is if the button is pressed, then change state to on. So the condition here, the button is pressed, right? So while we are in the state off and the button is pressed, we will change the state to on. Similarly, for the egg, the condition here is if 4 minutes in boiling water. So if the egg is 4 minutes in boiling water, the system will transition from the state raw to the state soft boiled. How do we represent transition graphically? Transitions are represented as arches going from one state to the other one. And we show the condition as the arrow here. So here we have an example of the switch again, and we have two transitions here. So the condition here is when the button is pressed, the system transitions from switch off to switch on. Again, when we are in the state switch on and the button is pressed, the system transitions from switch on to the switch off state. Okay, let's enhance our example with the switch with transitions. So when the system is in the bottom state, the light is off. If we flip the switch, we want it to transition to the state top. So we can add the transition here, going from state bottom to state top, and the condition here would be if the switch is flipped. So switch flipped. Right? So if we are in the bottom state, we flip the switch, we transition to the top state. Similarly, if we flip the switch again in the top state, we will transition back to the state bottom. So we have second transition which has the same condition, and that's it. That's that the switch was flipped. Right? So that's how we can model this switch using states, activities, and transitions. Another term, action. Action is one-time piece of work associated with transitions. So before we had activities that were associated with states, and now we have actions, and actions are associated with transitions, and it's one-time piece of work. So this activity happens only once, exactly at the moment when the system is transitioning from one state to the other one. So for example, for the switch, if the button is pressed in state off, change state to on and turn the light on. So the action here is to turn the light on, and this action happens exactly at the moment when you flip the switch. So it's associated with the transition. For the egg, it might be modeled as if The egg is 4 minutes in boiling water. Change the state to soft boiled and make the white hard. So the action here is to make the white hard. Right? So those are actions associated with transitions. How do we represent actions? We write them on the edge together with the condition. The condition comes first, and then on the next line or after a slash there is the action. So here we have two different transitions. Both of them have the condition button is pressed, but the action is turn the light on. So when we are in switched off, we press the button, we will transition into state switch on, and we will turn the light on. Similarly, for the other press, when the switch is when the button is pressed in the switch on state, the system will transition to the state off, and it will turn the light off. So these are the actions. So let's have a look at the switch again. So we modeled the behavior using activities before. Activities are the pieces of are the continuous work done in state. So what if we want to model this system using actions? Let's try to change it. First, make a backup. We will make a backup of our old system. And so now let's delete these activities from states. So now we have the state machine. Now we have the state machine without activities or actions. So let's add some actions. So when we are in the bottom state and we flip the switch, we want to transition into top and we want to turn the light on. So here it will be the action on the transition will be turn the light on. Similarly, when we are in the top state and we flip the switch, we want to turn the light off. So the action with the will be turn light off. So now this system has the same behavior as the system before, but this system is implemented using actions, and the other system was implemented using activities. So there is a special kind of transitions, and those are self-transitions, or in other words, loops. This transition has the destination the same as origin, so it does not change does not change the state, but it can have an action associated with it. So here is an example of a simple counter that counts a number of button presses. So this counter has only one state, and that's to be ready for key press. So when the button is pressed, in this state, we will increase the counter, so that's our action, and we will return to the original state where we are ready for next key press. So this is a self-transition. It's a transition that has an action, but it does not change the state. Self-transitions are used to model one-time behavior while staying in a state. So that's it. That's all the terms we need to know in order to be able to use state machines to model systems. Now, to remind ourselves what we learned today. So first we learned about states. States describe the condition of the system. Then we know that the states can change, and the act of changing states is called the transitions. Transitions describe how and when the states change. Now, that can be work associated either with states or transitions. So we have activities. Activities are associated with states, and it's a long-term work that's being done while in the state. This work is done all the time as long as the system is in this state. On the other hand, we have activities. Activities are pieces of work associated with transitions, and they are one-shot jobs that are done while taking a transition. So we have both activities and actions, and on the example of the switch we saw that they are interchangeable. We were able to model the same system using actions or activities. So now it's up to the designer to choose whichever is more appropriate for the situation we want to model. And that's it for this video. In the next video I will do an example of modeling, and in the last video I will do an example of modeling button debouncer and show how to program this state machine in the code.